Ready? Go!
I can't.
No. Restart.
Come, Daddy. What? Scale of 1 to 10, how stupid was that?
0. That was the best thing. That was great.
All right. By the way, I cannot go back and watch myself do this kind of thing. I even thought last time when I did my little ghetto thing, I thought, am I going to go watch this? I can't do it.
I'll edit the vlog for you. So.
We ended with this on Friday. I had no chance to do anything except show you this. I didn't even derive it because it was like 207 or whatever. And so this is what we call this is the Nernst equation. You'll hear me say that a lot because I like to say it. The guy's name I love, Nernst. But anyway, this is a relationship between the cell potential. Now notice there's 2 epsilons there. There's 1 epsilon and then 1 epsilon naught, which there's a big difference between those 2. This is the epsilon, the cell potential under standard conditions. This is the table value of the cell potential, but it's only good if your concentrations are 1 molarity and or your pressures are 1 atmosphere. This epsilon, I knew that was going to happen, without the naught sign, that's under any condition, wherever you are in the reaction, that is what the cell potential is at that point in the reaction. So, and that's going to bring it to, well, if we're not at standard conditions, then we need some term to tell us where we are in the reaction. That's what that Q is doing there. The Q is the reaction quotient. We've done 4 chapters on equilibrium. I'm really hoping by now that you have some sense of what Q means. Go ahead and make that confused look. I'll just move on from there. Q is the concentration of the products over the concentration of the reactants. If we're at standard conditions, what would Q be? If we were at standard conditions, what is it? It would be 1. Yeah, because if it's products over reactants, then standard conditions means everything has a concentration of 1 molarity or a pressure of 1 atmosphere. So Q would be 1. And so if you're at standard conditions, then this whole second term there, 0.0591 over n times log of Q, all of that goes to 0. It's 0. And so you just have the epsilon equal to the standard. All right, now I have 2 examples of when we would use the Nernst equation we're going to start with today. I don't want to just say, here's the Nernst equation, move on to the next thing. We do have to know how to use this thing. So both of these are straight out of the book. They're Zumdahl examples, and they'll both have their own thing. So we'll begin with this one. You're given the line notation for a reaction. Calculate the cell potential after the reaction has operated long enough for the zinc ion to have changed by 0.2 molarity. I'm just giving you a moment to read and digest the problem. We'll go through this one together. You can sit over here on Lauren's seat, but that means you'll have to be by Jane. Oh, you can't even see. Now, this reaction started at standard conditions. It didn't ask us to find what the cell potential was then. It asked us to find after the reaction has progressed some. Well, let's see if we can make some sense of this problem. First of all, we're given the line notation. How are you feeling so far about line notation? Feel all right about it?
Yeah.
Yeah? Line notation always writes things in the same order. To the left side of the double vertical lines is the anode, what you're starting with in the anode, what you're ending with. And over on the right side is the cathode, what you're starting with and what you're ending with. So underneath each of these, just so I don't leave anybody wondering where I got these things, I'm going to take the moment and write what the half reactions are. This is an oxidation because it's at the anode. So it's zinc yields zinc plus 2 plus 2 electrons. And then over here on this side, we have a reduction because it's the cathode. It's copper plus 2 ions. Reducing means it's gaining electrons. Plus 2 yields copper. This is an oxidation. This is a reduction. So we can add these two reactions together, and we'll have an overall balanced equation. Now, the reason that it'll be balanced is because this number of electrons given off equals this number of electrons taken in, yes? So now I can just add those two together. The electrons have to be equal before you add them together. Which reminds me, I completely blew off in the Nernst equation that n term, didn't I? Did we have an n term before, though? I thought we did.
Yeah.
We had another equation that had an n term in it. Yeah, so n is the number of moles of electrons. Essentially, how many electrons are transferred from the oxidation to the reduction? That's what the n means. And we'll go through that when we do these examples. In this problem, the n value was going to be 2. Because the oxidation is giving off 2 electrons, the reduction is taking in 2 electrons. They have to be the same, and whatever that number of electrons is the n value. Okay, so we have zinc plus copper plus 2. There's our reactants of this thing when I add these two reactions together. And then we have zinc plus 2 and copper. So very simple chemical reaction. The question is, what is the cell potential after the reaction has operated long enough? Okay, so the zinc ion initially, would we all agree that initially zinc ion has a concentration of 1 molarity? That's not what it is at the end, but that's what it was at the beginning. So the zinc ion is over here as a product. It was 1 molar. The copper ion was a reactant. That was 1 molar at the beginning. Now the Zundals are the ones that wrote this problem, unless they got it from somebody else. They did something kind of sneaky. They didn't tell us whether the zinc went up or down. They just told us that it changed. How do you know whether the zinc goes up or down? Emily?
Because it's a product, so it has to go up.
Yeah, this arrow right there, see that arrow? What do you notice about it?
Going to the right.
It's a one-way arrow. So this reaction only goes that way. Yes? That's how we know. So yes, in a reaction that has electrochemistry, the reactants have to go down, the products have to go up. They did this on purpose. They could have said the zinc increases by 0.2, but they didn't. They wanted you to know what happens. I'm not a mind reader. I've never talked to the Zundals. I assume that they did that. I don't know that for sure, but I mean that is what would make sense to me, is that they did that on purpose. So the zinc changed by 0.2. Does that mean it changed, and I should put 0.2 molarity there for its final concentration? No, it changed by 0.2. So it has changed up to 1.2 molarity. And what happened to the copper ion? It had to have gone down by 0.2. Whatever the stoichiometric ratio is, it's a 1-to-1. So if that went up by 0.2, this goes down by 0.2. This is going to provide us with the Q value. I don't care about zinc because it's a solid. I don't care about copper because it's a solid. Only the aqueous things and gases matter for Q or K, right? Okay, so now, over here off to the side, we'll use the Nernst equation. We have epsilon equals epsilon 0 minus 0.0591 over n log of Q. All right, so what did we just find? We found what we could use for Q. That's that. 1.2 over 0.8 is Q. Take the log of it. We decided we know what n is. N is 2. 2 electrons are transferred. What about this term? We're trying to find the cell potential. Find this thing right here. But that means we need that. How do we get that? You need to use your table. Right. Would you go ahead and grab your table? I think you need to go to a 5-period day, Jane. How are you in 5th hour?
Sometimes I eat
I wonder if lunch is hitting you. After lunch, you.
No, I eat in 4th hour because I get too hungry.
Yeah.
And I don't eat too much.
When you have the cell potential, the standard cell potential, yell it out. Zinc is oxidizing, so you have to find the zinc half reaction and turn it around.
1.1.
It is, yeah. Oxidation potential for zinc should be positive 0.76 after you turn it around. Yeah? You see it? And then the reduction potential for copper is 0.34. So add those two together. You get 1.1 volts. Okay, so now we have everything we need to solve for the cell potential for this thing. When this was at standard conditions, the cell potential was 1.1 volts. And that's what it would have been at the beginning, because we had standard conditions at the beginning. Now that the reaction has a chance to proceed, it has changed by 0.2 in favor there and 0.2 to the deficit there. We now can find what the new cell potential is. So it would be 1.10 volts minus 0.0591 over 2 log of 1.2 over 0.8. What do you get?
1.095.
Wow! The voltage sure changes, doesn't it? When it was standard conditions, it was 1.1 volts. Now it has gone way down to 1.095.
Oh.
I thought you were amazing.
It's amazing how much it changes.
What is this?
It's on the blog.
Now we do have to change it to 2 sig fig, so I'm just going to call it 1.09 just so we can see it change. But yeah, the cell potential. So yeah, it takes a while for the voltage to really start changing. But now you do see that the voltage went down. Let's just see if we can come up with a general understanding. Looking at the Nernst equation, I'm going to go back so we have a nice clean version of the Nernst equation. As the reaction goes to the right, and we have changed by more than 0.2 or more than like 1/5 of the original concentration. As the reaction goes to the right, what's happening to Q? Is Q getting bigger or smaller? As the reaction goes to Q is getting bigger. So the log of Q is getting bigger as well. We're taking this whole thing that's getting bigger, and subtracting it from the cell potential. So what's happening from the standard cell potential? What's happening to the overall cell potential as the reaction proceeds and keeps going and going? The voltage is going down. Right. The voltage is going down. Eventually, the reaction stops. Maybe we run out of one of our reactants, or the reaction comes to equilibrium. What do you think that number is going to be if we come to equilibrium? It's going to be 0. If there's no reaction, there's no more transferring of electrons, then the cell potential is 0. Yep. Okay. So that's what we're up to with the Nernst equation. I got one more example, and then we'll try on something else. There's another Zoomdall question, because they're masters at questions.
Do you want the text one?
Oh, thanks. Yes, I will. If you have yours. Thanks. Again, I want you to just take a look and digest the question.